All right, this is the chapter 26 notes. These are over sound. Nice little tuning fork here. These will cover sound and how sound travels. Okay, all sounds are produced by the vibrations of materials or objects. When you come to class on Thursday, I'll have some tuning forks and we'll talk about how sound is transmitted. You can see about what they have with the tuning fork here. Those little dotted lines are supposed to be how the sound is transmitted. So all sounds are produced by the vibrations of materials around them. So basically sound is transmitted through a vibrating object. Here are some different instruments that produce sound. A saxophone uses a vibrating reed to produce sound. Your voice is the vibration of your vocal cords. A piano or a guitar will use vibrating strings, where a flute will use a fluttering column of air at the mouthpiece to help produce the sound. Okay, pitch. This is the subjective impression about the frequency of a sound. This means subjectively. Each person could hear the sound differently, or the pitch differently, and say that it's different. We normally hear between 20 and 20,000 hertz. So the normal average range of people is 20 to 20,000 hertz. Again, for pitch, the key point here for it is subjective. All right, here are sounds. Infrasonic sounds are sound waves that are below 20 hertz. So below 20 hertz. Ultrasonic sounds are above 20,000 hertz. We cannot hear ultra or infrasonic sounds, but some animals can. There are animals out there that can hear below 20 hertz and above 20,000 hertz. Sound is a longitudinal wave, meaning it travels like this. It is not transverse. It is longitudinal. So the one's going parallel to the direction of the wave. So this is a big thing for you to remember. Sound is longitudinal. All right, sound is also a pressure wave. Because of the longitudinal motion of the air particles, there are regions in the air where the air particles are compressed together and other regions are where the air particles are spread apart. These have special names: compression and rarefaction. Compression is a pulse of compressed air. When you quickly open a door, it pushes the air that direction. So many of you may have seen this. When you open the door in one room, it might close the door in the room away from you or move the curtains away from you because you're creating compressed air there. In the tuning fork that you have here, you're going to have compression in the middle of this. Basically, in this area in here, you're going to have compression. Rarefaction is a disturbance in air in which the pressure is lower. When you shut a door, it pulls the air towards the door. So whenever you look at the tuning fork down here, you're going to have rarefaction on the outside. The pressure is less than normal. So in the middle here, you're going to have compression. And then on the outside, you'll have the rarefaction. The outside has rarefaction. For all wave motion, it is not the medium that travels across the room, but the pulse that travels. I said this a little bit in class the other day. When I talk, my voice box is what vibrates. And those vibrations of my voice box vibrate the air molecules around it. And the wave travels through the air molecules to your ear. And then that vibrates your eardrum, and that's how you hear the sound. Transmissions of sound. Air is the slowest at transmitting sound. Water is in the middle, and solids are the best. Basically, what we're saying is those particles that are closest together will transmit sound the fastest. Since air molecules are the furthest apart, they transmit sound the slowest. Water molecules are in the middle. And for a solid, the molecules are right up next to each other, so it's much faster at transmitting sound. The speed of sound in dry air at 0 degrees Celsius is about 330 meters per second, or about 1,200 kilometers per hour. This is about 1/1,000,000th the speed of light, which we're going to get into in the next chapter. So speed on average travels about 330 meters per second, but it can be anywhere from 330 up to around 380 meters per second. This is the reason why that you see lightning before you hear thunder, because lightning travels at the speed of light, which is 3.00 times 10 to the 8th meters per second, where sound is only around 330 meters per second. An increase in the temperature of water vapor will increase the speed of sound. For every degree increased, sound will travel faster by 0.60 meters per second. So the hotter it gets, the faster sound will travel. That's because the air molecules will travel faster and faster as you heat them up, allowing the sound to be transmitted faster. The speed of sound through materials depends on the elasticity of the materials. Basically, how elastic the material is. So basically, can the sound transform through it without making it to deform the medium that it's traveling through? So elasticity is the ability of a material to change shape in response to an applied force and then resume its initial shape once the distorting force is removed. So basically, when you throw, say, instead of sound, let's talk about water. If I throw a rock in water, it makes ripples in the water. But does the water stay deformed once I throw the rock in it? No, the wave will pass through it and then go right back to doing what the water was doing before. The same thing happens when you talk and your voice box is vibrating the molecules in the air. The wave passes through it and then the air molecules go back to doing what they were doing before. Steel is very elastic and putty is inelastic. In elastic materials, the atoms are relatively close together and they respond quickly to each other's motions. Sound travels about 15 times faster in steel than in air and 4 times faster in water than air. The intensity of the sound is proportional to the square of the amplitude of the sound. It is measured by what's known as an oscilloscope. On page 394, they talk about this in your book. And so we're now starting to talk about intensity of the sound, how loud we hear the sound, basically. Loudness is a physical sensation sensed in the brain. It is subjective, but is related to sound intensity. And different people will hear the same sound differently because it is a physical sensation. Their brains can pick up loudness differently than others. Younger people and older people sense loudness differently. It is subjective to the listener. The unit of intensity for sound is the decibel. Have we heard of the decibel levels? And so we rate sound by decibel levels. The older you get, you lose your hearing. We said before that you start out hearing an average between 20 hertz and 20,000 hertz. But as you get older, it comes more towards the middle. So you start going up from 20 to 30 to 40 to 50, and you start coming down from 20,000 to 19,000 to 18,000, and they start moving inward from there. And the rate of decay of hearing is actually happening at a quicker pace, and I bet you can't guess why. It's the earbuds. Earbuds are bombarding your ears with more and more sound, and also with the headphones, but it is causing people to lose their hearing much quicker these days. Decibel ratings. It starts at 0 for the hearing threshold. So the threshold of hearing we call 0 decibels. Then it goes to 10 decibels, which is 10 times as intense as 0. And then to 20 decibels, which is not twice as intense as 10 decibels, but 10 times as intense as 10 decibels, or 100 times as intense as 0. So it goes by factors of 10. So 0, 10, 20, they go up by factors of 10 each time. So it goes up by factors of 10. 10 times 10 is 100. Here's a decibel level chart just to let you see. 0 is the threshold of hearing. Then you go 20, between 20 and 40, about 30 is a whisper. Between 40 and 60 decibels is normal speech. 60, 80 is a lawnmower. 80 to 100 is an alarm clock and then lawnmower. 10 to 120 is a chainsaw. 120 to 140 is a jet engine. After you hit about 120 or so, this is known as the threshold of pain. Yes, it is called the threshold of pain. This is where you start to really do damage to your ears, right around this level. Here's another chart with this. Here's your threshold of pain again, right around in here. And it's got different, and the threshold of hearing again is right here. And this is normal sound, and you start doing damage here to your ears. Alright, forced vibration. This is vibration of an object that is made to vibrate by another vibrating object near it. So basically, one object is caused to vibrate by something else vibrating close to it. That is called forced vibration. The sounding board in a musical instrument amplifies the sound through forced vibration. A guitar would be barely audible without the sounding board. All stringed instruments use a sounding board. You know what a violin, a guitar, any of these things, the basic wood piece to it is a sounding board, and that amplifies the sound that the vibrating strings are making. Natural frequency. This is the frequency at which an elastic object, once energized, will vibrate. Basically, everything has a natural frequency. My tuning forks that I have all have natural frequencies, and when I hit them, they will vibrate at that natural frequency. Now we get into resonance, which is a big topic usually on the tax test. It means to resound or sound again. Radio stations tune into a certain frequency and resonate at that frequency. When you're dialing in your radio and you hit those different, like 102.1 or 96.3 or whatever radio station you listen to, when you dial into that, the radio station is resonating on that frequency, allowing you to hear it. Resonance is big because objects that have the same frequency, if you hit one of them, the other object will also start to vibrate, and I'll show you an example of this in class. In 1831, an infantry troop marched across a bridge and caused the bridge to collapse. They marched at the natural frequency of the bridge, causing it to resonate and fall. Now military personnel do something called breaking step when they cross a bridge, so not everybody is stepping at the same time on the bridge. All right, interference. This affects the loudness of sounds through constructive and destructive interference. We talked about this in chapter 26 notes. It can affect sound also. It happens in all waves. You can have it with light, you can have it with sound, anything like that. Beats. This is the periodic and repeating variations in the loudness of sounds. If you play an instrument with a group of people, you may have heard this sensation. If you are playing a note and somebody else is right next to you trying to play the same note, but it's not quite there yet, it's a slightly off frequency from the note you're playing, it'll sound kind of like a curve while it's going wow, 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 wow. It'll come in and out of phase, is what it sounds like, until they get right on the same frequency that matches you. All right, important note, the graphs on the following page represent sound as a transverse wave. This is for a better understanding of the concept. Remember, sound is a longitudinal wave. So these are just some graphs trying to show you basically where you have compression and rarefaction in the graph. So you see all these as it's spread out and you get compression and rarefaction in certain areas.